I'll go through a very brief introduction to the subject that we are going to study in this semester. And we'll start with a block diagram of a typical communication system. The typical communication system starts with the concept of a source of information, which outputs the information of interest which you want to send somewhere. Typically, this information will first have to be converted into electrical form through an appropriate transducer. This source of information, after its electrical conversion, is given to the system, some equipment, which at the moment we will simply call a transmitter. And the job of the transmitter is to prepare this information for actual sending through some physical channel, some physical medium through which the propagation of the information has to take place. So in a sense, the transmitter matches the characteristics of the signal which is coming from the information source to the characteristics of the medium through which the information has to be transmitted, so that efficient transmission is possible. I'll elaborate on this point a little further after a few minutes. And the information is now ready for putting on the channel. The physical channel, the physical medium through which we transmit this information, we'll call the channel. So channel is an abstraction for every kind of physical medium through which you will transmit information. At the other end, at the receiver end, well, at the moment I will not go into details. We will simply say that you have a receiver whose job it is to ensure that the information is given to the information user in a nice form, so that he can interpret it properly, or he can use it for whatever purpose he wants to use it. Right? So really speaking, in a communication system, there are these 5 major blocks, of which the most important parts are, most important components are information source, transmitter, channel, and receiver. Right? The job of the receiver, as I just mentioned, is to undo some harmful degradations that might have taken place while the signal was being transmitted through the channel. Also, additionally, it will try to amplify the signals, because typically the signal will attenuate as it propagates. But in addition to providing simple amplification, it also has to remove noise. It has to remove other kinds of interference about which we shall briefly talk in a few minutes. Right? So this is a typical block diagram of an information communication system. Now, what I'd like to do now is spend a little more time on each of these blocks so that you get a better feel for each of these aspects of communication engineering. Let me first start talking about information source. There can be many kinds of sources of information. Right? Our speech is one kind of information. Right? The most commonly used information source is voice, because human communication 90% of the time takes place through voice communication. So voice or speech, it forms the bulk of information communication that takes place. Right? So right? Then of course there is picture transmission. Picture transmission could be in the form of television signals, which is essentially moving pictures, moving at the normal pace at which light goes on, right? It could also be still pictures. For example, facsimile. I think I got the spellings wrong, but never mind. So this is transmission of pictures. It could be data from computers, from and to computers. Right? Now, as I was saying some time ago, the kind of communication system that you would like to design would depend on what is the information source that you're working with. Whether you're working with voice, music, audio, TV, facsimile, data, whatever, right? Because each of these kinds of information source has different kinds of requirements from the communication system through which it must be passed so that effective communication can take place. So I'd like to spend just a few minutes on giving you a feel for the various kinds of information sources that I just mentioned. Right? The data, this is not an exhaustive list, but more or less it captures the essence of various kinds of information, various types of information that you use. For example, you will also, the data that I'm talking about here may not be from a computer. It may be data that you are measuring by using telemetry instruments, right? You will be measuring the parameters of the ocean floor. You put some devices there, right? And that device produces, let's say, the data about the temperature of a particular layer in the ocean as a function of time. It produces that information, and through some kind of a communication system, it keeps on transmitting that information to an offshore station. Right? Maybe on a ship or maybe on the shore itself. Or it could be telemetry from in free space or on some satellite or whatever. So let's talk about these information sources in some more detail. And I'll start with, as I said, one of the most common sources of information for us, which is voice or human speech. Now, one of the important features of information sources which will be particularly relevant to the discussion on communication systems is spectral band, right? It's spectral occupancy. I believe you all are familiar with the concept of spectrum of a signal, right? Spectrum of a signal is nothing but, well, in a very rudimentary sense, the Fourier transform of the signal. If you have a time domain deterministic signal, then its spectrum is just the Fourier transform of the signal. Of course, the Fourier transform of a real signal in general would be a complex entity, right? It will have a real part and an imaginary part, or a magnitude part and a phase part, right? So we can talk about an amplitude spectrum, which is a plot of the amplitude of the various frequency components as a function of frequency, and it could be the phase spectrum, which will be a plot of the phase angles of the various frequency components as a function of the frequency, right? If it is a non-random, it's a non-deterministic signal. If it is a random signal, it is usually better to talk not about the spectrum of the signal, but about the power spectrum of the signal, right? I believe you at least are familiar with these terms, right? At the moment, that familiarity is all that I'm requiring for talking about these concepts, but we'll take up these issues as and when required later in more detail. So, as I said, spectral occupancy of a signal is one of the important attributes that we need to look at when we're talking about communication signals, right? And for a speech signal, for the human speech signal, I'm saying human speech as if we have other kinds of speech, but I think who knows, maybe there are some kinds of animals also who speak to each other, like in Dr. Dolittle or something, but I don't know about that. We're talking about our speech here. Right. So we see that the spectrum has this kind of a nature. It builds up from low energy at the lower frequency end. So this is typically the notation for power spectrum, S of omega, as a function of omega, right? So this what I'm plotting here is, so if I plot power spectrum, then there is no question of phase in the, because power spectrum only gives information about the distribution of power as a function of frequency, right? Signal power as a function of frequency. And typically this is the tool that we employ when we're talking about random signals. And if you model speech as a random signal, it's not really all that random, although there is randomness in it. One can see that the power spectrum looks something like this. Builds up to slightly lower energy at the lowest frequency end. Builds up to some peak values, peak energy at about a few hundred hertz, which will vary from speaker to speaker, and which will vary from the information that you are speaking, with that information. So this spectrum is not really fixed, right? It's just a typical plot that you might see. So as you see, there will be a few major peaks in the spectrum, but on the whole, the spectrum will start decaying after a few hundred hertz. And for telephonic communication, it is found that if you concentrate on the energy between 300 hertz to about 3300 hertz, right, you capture most of the intelligence as well as essence of speech, right, without losing much on either the intelligence or the let's say the quality of speech, right. So for most telephonic communication purposes, the band from 300 hertz to 3300 hertz is the one which is important, right? So that is why we say that a voice band channel has a bandwidth of about 4 kilohertz. That 4 kilohertz includes some guard band, some additional frequency band, to make sure that we don't lose anything, right? So typically, the bandwidth of a speech signal is regarded to be less than 4 kilohertz. But I must mention, this is not the actual bandwidth of the speech signal, right? Actual bandwidth, the actual energy plot extends beyond this and goes on up to about 7-8 kilohertz. If you want really good quality, studio quality speech to be heard, you must process that entire band properly, right? But this is the standard values that we take in telephone communication. It's found to be adequate, right? Now, before I leave this signal, I'd just like to say a little bit more about it, right? What can I say more about it? I'd like you to know that speech signal is a highly studied kind of signal. It's a signal which has been extensively researched, right? For various reasons. It has been researched by linguists for their reasons to understand the nature of languages, the way they are spoken, the way they are perceived by people. So it has that kind of background studies done on it. But from a communications point of view, we will learn somewhat later that the amount of information that is being conveyed by a signal is not necessarily proportional to the bandwidth of the signal, right? The signal may have a very large bandwidth, right? But it does not necessarily imply that it is conveying a lot of information to us. Now, why I'm saying this? Because again, this is related to the fact that we'll learn a little later that bandwidth is a very important attribute of a communication system. It's a very important resource. If a signal has more bandwidth, it will occupy more bandwidth somewhere in the spectrum of communication signals, and it will disallow other signals to be transmitted in that frequency band, because a frequency band is already occupied by this particular signal, right? And therefore bandwidth becomes a very important resource for us. For a communication engineer, as we learn, there are two main resources that we need to deal with. One is the bandwidth available to us. because a large number of people want to communicate to each other. Everybody has to work in some band or the other, and it becomes obvious that if they all start talking together, if they all start transmitting information in the same frequency band together, there's going to be a lot of problem, right? They're not going to be able to hear each other. They're just going to hear some junk, right? Which is not very desirable. So bandwidth is a very important resource for us, right? Similarly, amount of power that the transmitter outputs is a very important parameter in a communication system. You may have to transmit a large power if you want to send a signal to a large distance, a long distance, right? But at the same time, a large power output of a transmitter is not necessarily a very nice thing to do, right? Not that it implies that you have to have a lot of power at the transmitter, which also becomes a limitation sometimes. For example, if the transmission is taking place from a satellite, right, that you have sent up there, and the amount of power that is going to be available to you for sending is going to be limited by the power that you have on the satellite, right? So at times that is a limitation. But more importantly, when you put a large power in the transmitter output, it has the potential to interfere with other signals, much larger number of other signals over much larger distances, right? So therefore power is a very important resource. The smaller the power that you use, the better and more efficient your communication system is. Yes, please.
Once I fix a bandwidth,
yes,
a particular frequency, why is it interfering with how much of a power I introduce? I have a fixed bandwidth for a particular frequency, how can I interfere with some other signal?
Good question. The question is, if I have already fixed the bandwidth of a signal in which no other signal is being transmitted, how it can be a source of interference for others? Well, I will come to this issue a little later, but right now I can say this much. That particular band that is allotted to you is typically allotted to you for operation in a certain area, right? But if you transmit it with very large power, you will have a significant component of that frequency in a relatively distant area also, where that frequency band has been allotted to somebody else, right? So therefore it has the potential to interfere, right? So at the moment I'll only say this, but I'll come back to this point. Right. So the original point that I was making, from which we digressed, was that bandwidth is an important resource. Communication signal has a bandwidth of 4 kHz. The voice signal has a bandwidth of about 4 kHz. But it does not necessarily mean that the information conveyed by a voice signal when I'm talking to you is proportional to 4 kHz, is of this order. Because this bandwidth is a property of a waveform, speech waveform, that is coming out when I'm speaking, right? But the actual amount of information that I'm conveying to you is something different altogether, right? In fact, it is in terms of bits per second as a measure of information, it is a really very small amount. It's something like 100 bits to 200 bits per second of that order, right? Which, as you can see, is very, very small as compared to 4 kilohertz, right? This is 4,000 and that is 100 to 200. The orders of magnitude difference in the amount of information that is being conveyed to you, or information rate that is coming out, and the rate of variation of the signal itself, right? The actual rate of variation of the signal itself. So this is very important, because this means that maybe by just sending the raw information, raw waveform, I'm not doing the most efficient kind of communication in terms of bandwidth requirement, bandwidth system. And for this reason, communication engineers have studied these commonly used kind of signals very, very in great depth to understand how we can transmit information by using bandwidth much less than 4 kHz, by exploiting our understanding of how a speech signal is produced by the human body, right? Seeing what the attributes of that speech production mechanism are, and then transmitting only those attributes rather than the actual waveform. And that in the process you'll be able to do a much more efficient communication than by just transmitting the raw waveform itself. But that's a more advanced way of looking at a source. Right now, I just wanted to say this much, right? So we'll return to this point later if required. Now let me briefly talk about some picture signals. The two kinds of picture signals that we have talked about is the TV signal and the facsimile signal. Right? The TV signal is a moving picture signal. Right? So when it is a moving picture signal, you have to make sure that you don't lose the essence of motion itself. Right? So typically, as I said, you have to first convert this signal into an electrical signal, which will be done through a TV tube, a TV camera, which will, through an optical lens system, capture the picture and then somehow convert this into an electrical signal and scan that electrical signal, let's say line-wise, to convert this into a one-dimensional signal. But otherwise, TV signal is a two-dimensional signal. Right? It has two spatial coordinates. But ultimately what I'm going to transmit is a time signal, signal of time. So I'll convert this spatial information into temporal information by scanning this information, right, line by line, and transmitting it. And I must make sure that the time taken to scan a picture, right, complete picture, line by line, is sufficiently small so that I don't lose if the picture changes because of motion a few seconds later. Right? I must be able to capture the motion also. So I must be able to scan sufficiently fast, right? I must scan sufficiently fast so that I don't lose the essence of motion also. Right? Otherwise it will look like a transmission of a few still pictures, one after another, rather than a moving picture. Right? So that's very important. And it's therefore clear that the scanning will be fast. And if the scanning is fast, it essentially means that the signal that you will be transmitting will have a large bandwidth. Right? Because bandwidth is related to the rate of variations in the signal. Right? If you are scanning at a very fast rate, it will lead to a large bandwidth signal. Typically, it turns out, I'm just giving you information, and this is a good point for comparison with the other signals. For a TV signal, the bandwidth requirement is to the tune of 4.5, not kilohertz, but megahertz. Right? So as you can see, that it's 3 orders of magnitude higher than the bandwidth of a speech signal. Right? The bandwidth requirements of a picture signal will be much higher than the bandwidth requirements of a voice signal. And therefore, a communication system that you have designed for transmitting voice signals will be of absolutely no use to us when it comes to transmitting TV signals. Right? Picture signals. On the other hand, if I'm transmitting still pictures, I have less constraints. There is no requirement that I must scan it very fast. Right? I can scan it slow. Make it compatible with the bandwidth that I have available in the communication system. Right? I can scan it sufficiently slow. Because there's no requirement that there's no requirement that by the time I scan it, the picture might have moved somewhere else. Right? The action might have moved to some other action. Okay? The picture is still there, the same picture. So I can scan it slow. Right? And that's precisely what you do in a facsimile signal. Right? And that's the reason I can transmit a fax signal through a telephone line, which is designed to carry only 4 kilohertz of bandwidth. Right? Because the rate of scanning is under my control. Right? And there is no particular hurry from the point of view of the nature of the picture that I want to transmit to scan it fast. Of course, if I scan it fast, there's an advantage. What is the advantage? I'll occupy the communication resource for less amount of time. I'll pay less amount of bill, right? If I scan it fast and send it fast. That is there. But from the nature of the picture itself, there is no such requirement. Right? I can scan it sufficiently slow so that at least it's possible to transmit it through this channel. And that's why facsimile transmission is possible over the telephone line, whereas TV signal transmission is obviously not possible over the telephone line. Right? Although there are new techniques which will again compress, just like I talked about the compression of the bandwidth of the speech signal, it is similarly possible to compress the bandwidth of the picture signal. Right? Because once again, the amount of information conveyed by the picture or moving pictures is not proportional to this bandwidth that we are going to use for it. So it is possible again to use to compress this bandwidth and use the communication resources more efficiently, right? So it's possible, but that's again an advanced topic, and we'll not discuss it now. So I think this much discussion about the information sources for the moment is good enough, except that let me say one last thing about the data sources. Right? The sources that I've discussed so far are basically different from this source in one major way, and that is they are analog sources. Right? We understand the difference between analog and digital. Today, this age, of course, understands it too well. Right? An analog signal is one in which there is continuous variation. So these are all analog signals. And this is basically digital, but I'll come back to this digital issue again in a few minutes. So by analog, basically what we're saying is, if you look at the signal as a waveform, as a function of time, there is a continuum of ranges of amplitude. The amplitude of the signal at a given point in time can be any real value, right? Theoretically, any value from minus infinity to plus infinity, but even practically any value from, let's say, from minus k to plus k, right? So it could be a value like 4.923, right, or whatever. So you can have any real number as the value. Whereas in a digital signal, the values that the signal can take are just two. Let's say 1 or minus 1, right? So if the signal can only take a binary set of values, or in more general terms, a discrete set of values. Here it's a continuous set of values, any real number between one lower limit to one upper limit. But in this case, it could be 2, it could be 4, it could be 8, but it could be a set of discrete values, right? The binary case is an example. But it could be 4 array, it could be 8 array, right? It could have 8 levels, or 16 levels, or 256 levels. The moment you have that, it becomes a digital signal, right? So that is one essential difference between these three previous sources of information that I talked about and the data signals that we typically tend to use. However, we must remember that the physical world, particularly the physical medium through which you are going to transmit information, is not digital in nature, right? The physical medium, the free space, the cable, right? It looks at the signal as a voltage waveform as a function of time, right? And it hardly bothers whether it is a continuous range or it is a continuous range. This looks like a continuous thing to it, right? So it treats the signal in the same way. That is, and there's a small issue here. The issue is this really matched to the medium? It's not. The real medium is analog. It has some advantages. We have some advantages when we work with a digital formulation of our signal, right? But the advantage tends to get lost unless we keep in mind that the physical medium through which the information is finally going to be transmitted is still analog in nature. We have to keep that in mind even when we are transmitting digital information, right? So in digital communication, which is a follow-up subject of this communication, this is an issue on which we spend a lot of time. But right now, it is just a matter of just drawing your attention to this point. Okay. Before I leave the data signals, one last thing I'd like to say about it is the bandwidth requirement of a data signal is something that will depend on what will it depend on? Anything else? Okay, let me give you the answer. It will primarily depend on the rate at which you are wanting to transmit data, right? Because again, you see, as I said, the bandwidth depends on the rate of variations in a signal, right? Maximum rate of variations. So the rate at which you want to transmit ones and zeros, if that becomes large, the bandwidth requirement becomes large. So for data signal, I don't say, okay, it requires this bandwidth or that bandwidth or this bandwidth, right? It will depend on what is the rate at which you want to transmit information. Of course, people will say the highest possible rate. But then if you are ready to pay the cost for it, you can get the highest possible rate. Right? So everything has a cost associated with it. So you can have a low bandwidth data signal and you can have a high bandwidth data signal. It depends on the requirements on yours. Okay, so if you now come back to this block diagram, we have discussed to some extent the nature of the information source, particularly with reference to the bandwidth requirement. Alright? Now let's discuss a little more the issue of the transmitter. What does the transmitter have to do? Right? What are the basic functions of the transmitter? Okay. As I mentioned earlier, the basic functions of a transmitter have to do with the fact that you have to match the signal characteristics coming out of the signal source with the channel characteristics through which the signal will have to be actually finally transmitted. Right? Now what do we mean by that? Let's take an example. Let's say you want to use free space as a medium through which the signal is to be transmitted. Right? Now if that is the case, the transmitter will have to radiate information into free space. Right? Which essentially means it will have to have as a built-in mechanism an antenna here, right? Which usually schematically is denoted by this notation. This is the notation for an antenna. So this is a signal coming in and it radiates, right? This triangle is usually used to denote an antenna in a communication system block diagram. But physically, an antenna could be one of many types depending on what frequency range you are working with. Now, okay, the question is, so what? Now, let's say you're transmitting a voice signal, right? If you know some electromagnetic theory, perhaps you also know the fact that the efficiency of radiation of an antenna will depend on the size of the antenna related to its wavelength. You appreciate this fact? If you, for example, the wavelength is, let's say, 10 meters, wavelength of the electromagnetic wave that you're working with is 10 meters, right? Then for efficient transmission of information into the free space, you require an antenna aperture that is the size of the antenna at least of the order of 5 to 10 meters, right? Of this order. Now, I do not know whether you can quickly do one calculation. Let's say you're transmitting voice signal. What is the highest frequency component you have there? Let's say 3000 hertz, right? Or 4000 hertz. Can you make a quick calculation what will be the wavelength of this if it is seen as an electromagnetic wave, because you're electrically converting this into electrical signal and let's say amplifying it and putting it in the antenna. What kind of wavelengths do you have? Order of magnitude? 5 meters. Alright, so it's about 100 kilometers, right? So can you radiate it? Unless you have an antenna of that order, that size, it's simply impossible to read it, right? So you can see there is a problem here. I want to transmit a voice signal through free space by radiation, but the antenna size that will be required will be of a very, very large dimension, right? It will be simply not possible to have such an antenna, right? So what do I have to do? I have to make sure that this signal is first embedded onto some other signal for which the antenna size requirement is much smaller, right? So that's the concept of a carrier. So typically a transmitter would require as another input to it, in addition to the signal, another signal which we call the carrier. The job of the carrier is, as I mentioned earlier, the to carry this signal along with it, right? To carry the information signal along with it. Typically, not always, typically a carrier is a pure sine wave signal of a suitably high frequency, right? Why high frequency? So that it is easy to design an antenna which will be able to radiate it, right? And so therefore what you do is you have to that brings us to what the transmitter has to do. The transmitter has to put this information appropriately or embed this information appropriately into this carrier, right? And typically this is done through a process of what is called modulation, right? You modulate a specific parameter of the carrier along with the signal. For example, the signal might modulate the amplitude of the carrier, right? Depending on what is the amplitude of this analog signal here, you modify the amplitude of this carrier. So amplitude of the carrier now carries the information, and you get a communication signal which looks maybe, so suppose this is your basic information signal as a waveform of time. So I'm not be able to draw very precisely, but the modulated signal will look something like this. Right? So this amplitude of the signal as a function of time is the same as your information signal. So the transmitter has to do this job of converting that information signal which looks like this into a signal which looks like this. Is it clear? And that operation is called modulation. Now, it's not necessary that you modify the amplitude. You could modify the phase, you could modify the frequency, instantaneous frequency of the signal, and so on and so forth. Right? All these are different kinds of modulation that we can have. Now, so that's the reason for modulation, using modulation. Modulation helps me to translate the spectrum of the signal, which was earlier lying in the band from, let's say 0 to 4 kilohertz, right? Where does the spectrum translate to now? What is the spectral occupancy of this signal? Let's say this carrier I choose as 1 megahertz. Right? It's a carrier frequency of 1 megahertz. Right? So the center frequency of this will be around 1 megahertz. Right? So you will typically have, of course I'm not showing the same thing here for ease of plotting. You'll get a signal which has a spectral occupancy in the neighborhood of 1 megahertz. Right? And this bandwidth 4 kilohertz is a very small fraction of 1 megahertz of the center frequency, right? So more or